Okay, great. So welcome, everyone. Today we'll have a 3-hour tutorial for this afternoon on deep learning, and it'll be taught by myself and Kai-Ming He, who will give the second half. So the way it will work is first I'll give a lecture on just the basics of what are neural nets, what are the kind of fundamental ideas around them. Kai-Ming will then talk more about some advanced architectures, the idea of representation learning, go into a little bit more applications like computer vision applications, and then we'll have a short kind of hands-on tutorial at the end of the session. For that hands-on component, I will share a Colab environment, and I'll go through it line by line and tell you a little bit about how you'd actually use something to do deep learning, which is going to be PyTorch. And you're welcome to follow along on your own computers. So if you don't have your laptop, that's okay. You can just follow on the slides. But if you do, you can use your laptop. And you'll need a Google account in order to do that, because to use Colab, you need a Google account. And for that session, I'll put the link to the Colab on the slides. OK. So yeah, let's get started. And also feel free to, I'll pause now and then to take questions. So feel free to raise your hand if you have a question as we go. OK. This lecture is, so I teach a deep learning course here at MIT, and this lecture is kind of pieced together from the first few lectures of that course. So you're seeing that content, at least the intro level of that content. OK. So we're going to talk about first a brief history of deep learning. What is this amazing thing that's happened? Then the basic formulation of neural nets, the idea of how you can do learning with a neural net, which is an optimization process, the basic layer types, and there'll be two in this first lecture, which are going to be linear layers and pointwise nonlinearities. Those are the two main types. I'll touch a little bit on the idea of approximation and generalization theory, which is kind of the main theoretical underpinnings of when and why does deep learning work. And then we'll talk about some of the data structures and what it looks like to actually work with deep nets. And I'll give an example of training a deep net to do image classification. OK. So let's start with a brief history. So right now, there's huge enthusiasm for deep learning. That's why you're all here. And actually, there's been a few eras of enthusiasm. So let's look at the history. So these things got started quite a long time ago, around 1950s, when cognitive scientists and biologists were trying to understand how the brain works. So the origin is, of course, actual brains, real neural networks. That's where the word neural network comes from. And the perceptron was one of the early models of how learning works in the brain from Rosenblatt in 1958. One of the kind of interesting things is if you go back in time, the field of AI and psychology, deep learning, and neuroscience, they were all the same field. So these papers were published in biological and psychological journals. There wasn't a field of computer science at that time. And we're starting to see that happen again. So we have a nice connection to, BCS is connected to this building. We're starting to again see that the study of intelligence can be thought of across different types of animals and machines and humans. OK, so perceptron looked like this. I'll go into the mathematical detail of how it worked a little bit later. But basically, it was a simple network of these models of neurons. And the way they work is they just they look at some input, like a digit or a letter A, and they take a weighted sum of what they're seeing. So every little sensor here, these are the inputs to the neurons. They look at, is the pixel black or white? And then they take a kind of a weighted sum. And if they see that sum, that weighted sum exceeds the threshold, they fire. And in this way, they can fire when they recognize a particular digit. And we'll look at that in a lot more detail. OK, but it's a simple model of a neuron that's meant to actually model how neurons work in the brain. OK, then some folks at some random university happens to have been here. They came along and threw some cold water on this, and they published a whole book on perceptrons. And basically, you'd think that this would be the book that would get everyone excited about neural nets. It wasn't. It was the book that kind of killed the field, because they proved that the perceptron, the basic neural net that Rosenblatt had come up with, was incapable of doing very complex operations. So they showed that the perceptron can only do kind of linear operations, and that was not really enough. It could do linear classification, but it couldn't do nonlinear classification. Okay. But then some other folks came along and said, wait a second, if we start making networks with more than one perceptron, like a lot of neurons, and stack them in layers, then we can do all kinds of processing. And we'll talk more about exactly what kinds of processing neural nets can do. It turns out they can do almost anything. And Rumelhart and McClelland and folks in the 1980s really pushed that forward. You may have heard of this XOR problem, a basic logical gate. A perceptron, the early neural networks could not represent an XOR, but if you stack two perceptrons in a row, then they can, or two sets of perceptrons in a row, they can actually solve the XOR problem. So people got really excited again, and that's when you had these folks like Jeff Hinton and Jan LeCun doing all their early work on neural networks, coming up with backpropagation and convolutional networks. Here's an example of a convolutional network. Kai-Ming will talk a lot more about how those work. But those became popular in the late 80s and 1990s, and they could really do interesting things. So unfortunately, we didn't quite have enough data or compute big enough GPUs to do what you see today. And so even though these early models had almost the same architecture and ideas as we currently will be using, they didn't quite have the computation behind them and the data behind them. And so people said, wait a second, these can only recognize digits, they can't do much more. And by 2000, there was another kind of AI winter or deep learning winter. So you had this oscillation again. So the Neural Information Processing Systems conference, which is called NeurIPS today, biggest AI conference around, in 2000, some people did a little study and they found that the words in a paper title that are most predictive of a paper being rejected are neural and network. And the words that are most predictive of a paper being accepted were these other older machine learning ideas, Gaussian and belief propagation. Okay, so these ideas are also still popular and coming back, but these ideas have become completely dominant in the next decade after that winter. And what really spurred the current excitement around deep learning and neural networks was this paper, the AlexNet paper. So you may have heard of the AlexNet moment or the ImageNet moment. So it was when this big neural network called AlexNet, made by Alex Krzyzewski and his co-authors, won the ImageNet challenge, which was a big challenge in doing image recognition. So it was essentially the same ideas as had been explored in the 1990s, but scaled up. And I was around when this came out, and Kai-Ming was around, and I think that it really was remarkable. It really was surprising, because here are the ImageNet images, and this network could, this looks like obvious just now. All of our phones can do this, no problem. But back then, it was like, you could actually recognize that that's a mite. The machine would say that is a mite. Like, that was one of these first signs of real, AI happening. And additionally, it was really, really fast. Like, I was working on computer vision back then, and we had methods that would take half an hour to analyze a scene. And this would run in less than a second and recognize an image. So it was fast, and it was more accurate than anything else. And it was also simpler in a way. Like, these networks are really, really simple in a certain sense. So we're going to get to appreciate that as we go on. Okay, so people got super excited. That's been the last decade of excitement. But keep in mind, there is this oscillating trend, right? And what is the period of that trend? It's about 28 years. So I might have to remake this slide in a few years, because we're getting pretty close to the 2028 period. And it hasn't quite gone down yet. But you never know what will happen. Maybe it will go down. Or maybe it will just go up. That seems to be what's happening right now. But things can't go to infinity, so probably something like that. Okay, so that's why everyone is so excited right now. These things are simple, they're fast, and they work really well. And I'm sure you have all seen in the news, and things that you use are all powered by neural nets doing amazing things now. Okay, so let's look at how they work. So they're essentially modeled off of biological brains, at least inspired by biological brains in the first place. And here's how neuroscientists think that the visual cortex in a human brain or a monkey brain will recognize images. So it will take in a photo on the retina, or photons coming into the retina, and then layer by layer in the kind of neural net layers of your brain, you will start to extract more and more complex patterns. So it's this layer by layer hierarchical processing, and there's pretty good neuroscience on how that works, and it matches pretty well with how deep nets, artificial deep nets, also are designed. Okay, so let's look at this problem of image classification, one of the most successful applications of deep learning so far. Okay, so we have our fish, and the computer vision folks will tell us that the way, the classical way to understand an image is first you extract edges and textures and colors, and then you do segmentation and you identify parts, and then based on the parts, it has an eye and it has a fin, and therefore it's likely to be a fish. You'll kind of aggregate all of your detected items into a single prediction that this is a fish. Okay, so we used to hand construct those modules, and deep learning has mostly replaced that process with learning those modules. So maybe we could learn this last mapping. We could say, given that we found an eye and a fin, I will try to learn a rule for deciding if it's a fish based on whether it has an eye or a fin. But maybe we can actually learn all of these arrows. And that's the idea of deep learning. And maybe we can make it this kind of very simple abstraction, which is just modules which feed one into another. And okay, let's make it deep. So let's make it more than just one processing module followed by another processing module, but quite a lot of processing modules. And this is the basic kind of motif of a deep net. You have a set of learned transformations going from an input to a prediction at the end. And this would be a case of image classification. And all of these arrows are going to be functions that you parameterize, and you're going to wiggle around the parameters until you find a setting of the parameters which achieves the desired mapping. Okay, so there's background to this whole field, which is machine learning and the idea of supervised learning. I'm going to give you the gist of that, and I think a lot of you have probably already seen that. So if not, just this will rely on a little bit of knowledge of machine learning to fully appreciate these lectures. But I'll try to give the gist of it on this side. So this slide. So this is like machine learning 101 with a deep net. So the way it works is we're going to try to fiddle with the parameters. The parameters are going to be labeled as theta. We're going to try to fiddle with the parameters until we find a setting of the parameters that will make it so when the input to the system is this array of pixel values, the output will be the label clownfish. It'll be a numerical output that represents the label clownfish. And the way we'll train this system, the way we'll decide on what the parameters should be, is we will have a big training data set of images and labels. So we'll have this fish and this label. We'll have a photo of a grizzly bear and the label grizzly bear. We'll have a photo of a chameleon. We'll have a million or more such paired input-output examples. That's the desired behavior, and we want to fiddle with the parameters until they output fish when it's a fish. They output the label that matches the training data. Okay, and just a little bit of mathematical notation for those of you that are comfortable with that level of detail. So we're going to try to minimize a loss function. The loss function is the error that we incur, kind of like a misprediction error. So it's going to be, here's my prediction of my network. My network is f with parameters theta. When f is applied to an image of a fish, it'll make a prediction. We compare that prediction to my true label in my training data y, and we measure how far off we are from the true label. And we try to find parameters theta, so try to find the parameters of the function that will minimize the losses incurred, the misprediction errors that we have made, summing over all of my training items for like a million, n equals a million training items. So this is kind of classic machine learning. This is supervised learning. That's how it works. And that's most of what we will be looking at with deep learning. Okay. So one of the key things to keep in mind is that all of machine learning and all of deep learning is just a function of the data that you have. Like it's the data is that fuel that allows you to find patterns and learn how the world works and cause cars to drive successfully and so forth. So you always want to remember that like the starting point is the data, and to make an image recognition system, you need to have a lot of examples that you can learn from of images and labels. Okay. Okay, so that is our learning problem. Our learning problem is minimize the loss over all of our predictions on our training data. Find the parameters that minimize the loss. So how can I find the parameters that minimize the loss? So one idea that you can use and would be perfectly fine if you had enough compute, enough CPUs and GPUs, would be just randomly set the parameters and see how well they work. Randomly choose another set of parameters, see how well those work, do that 1 trillion times or more, and then just report what is the best set of parameters that minimize the loss. That's perfectly fine, that will work, but it takes a lot of compute. So a slightly better idea is to intelligently fiddle with the parameters, not just randomly, and that's the idea of gradient descent. So we will take this objective, which is going to be measuring our prediction error, and as long as that is a differentiable function, then we can call it j, and we can take the gradient of that function. And so the way that gradient descent works is we have this cost function j, this loss function j that we're trying to minimize with respect to the parameters theta of our neural network. We initialize our neural network with some setting of parameters, and then we will simply take a step in the direction of steepest descent, which is just the gradient of this cost function j. Okay, so we'll start up at the top, and we'll just take steps, step by step, fiddling with the parameters in the direction that minimizes this loss. Okay, it'll look like that. Anyone see something that might go wrong right here? What might be an issue with gradient descent to optimize a neural network? Okay, we got here. What's going to happen? Yeah. Could get stuck in a local minima. What if it goes just like it's like a skier? What if it accidentally there's a little blip in the train and it goes off to this minimum? It might get stuck there. So yeah, gradient descent can get stuck in a local minimum. It doesn't necessarily find a global minimum. So it's just going to find a good solution locally that you can't improve locally. And sometimes, like in this cartoon I'm showing, it might find the global minimum of that function. An interesting thing about deep nets that we won't have time to fully justify is that they tend not to get stuck in bad local minima. There's ongoing theoretical work on why that is, but it tends to be the case that the minima that are found by gradient descent for deep nets are actually good solutions that are close to the global optimal solution. Okay, so don't worry too much about the fact that gradient descent gets stuck in local minima. That turns out not to be such a big issue for deep learning. Okay, so here is the picture of gradient descent. And mathematically, this is what it looks like. I have my parameter setting, which are the parameters of my neural net. We'll see exactly what those correspond to in a few slides. And I have my parameters. I'm going to update them. So I have my parameters at one iteration of my optimization. I'm going to make my updated parameters at the next iteration of my optimization by taking a step in the direction that will locally minimize my cost function that I'm trying to optimize. And there's one really important parameter. Everything is kind of automatic, right? It's just you're doing calculus here, and it's all kind of automatic. But there's one thing that's not quite automatic yet, which is this parameter, which is how big a step do I take? It's called the learning rate. Okay, so it's how big a step I take. In this graphic, the learning rate is how big are those arrows. And imagine that if I took really, really big steps, I would descend a lot faster. It's like I'm skiing really fast down the slope, but I might overshoot the minimum. I might take too big a step and go way off into some other completely different part of the loss landscape. Okay, and if I take little steps, then I actually will converge, theoretically. I'll converge to a minimizer in theory. But if I take little steps, I'll have to take a lot of little steps, and it's slower. Okay, so the one thing that we don't yet really have a good way of automatically setting is the learning rate. And this is something, whenever you do deep learning, you'll want to tune this parameter. This is kind of the most important hyperparameter of deep learning. Okay, so don't forget to tune your learning rate. Okay. Okay, so let's summarize what we've seen so far. We're trying to go through a lot of material, so this is going to be fast. But I want to pause to take a few summaries. So one, deep nets are compositions of simple functions. It's take data, do some function on it, do a function on that, do a function on that. It's a composition, series of layers. The standard way of training a deep net is gradient descent, fiddle with the parameters to move in the direction that optimizes your task objective, which would mean for image classification, achieves good classification performance. And the most important optimization parameter that you really do need to fiddle with is this learning rate. How big is the step size that you're going to take? And yeah, question.
Do you have any strategy to fine-tune the learning rate?
Yeah, is there any strategy to fine-tune the learning rate is the question. And the answer is yes, there's like a whole field of work around this. And I don't think it's yet really converged on a good solution. But the general strategy is you just try a bunch of learning rates. So you might call that grid search. You just try learning rates at kind of logarithmically spaced intervals. Like you try 2, and then 1/2, 1/4, 1/8, 1/16, something like this. Yeah. What's that? It's kind of manual. Yeah, you just try it. But you have a loop, which is so you try a bunch on some like small part of your data, and you see which one works, and then you scale it up. Okay. Okay. Any more questions, and then we'll move on. Cool. Okay. So that's deep learning at the level of just machine learning. Now let's dig in and see what are the unique properties of this architecture. What are actually these functions? What is their form? Okay? And the way I like to think of it, and I think Kaiming will get into this in more detail, is deep learning is all about representations. It's all about starting with one representation of your data and transforming that representation layer by layer through your network, through this composition of functions, to make it a better and better representation until at the very final layer of your network, your representation is something that you can kind of directly read off your prediction or your decision that you need to make, you need the system to make. So it's kind of transforming your data representation from raw data to something very usable that you can directly use. Okay. A name for this is representation learning. So deep learning and representation learning are often kind of thought of as going hand in hand. Okay, so what is this transformation from an input representation to an output representation in a deep net? So the most important main transformation, the main layer type, we call these layer types, is going to be the linear layer. So it's a linear transformation where we take in our data that we're processing, like our image or our other type of data. It's a numerical vector of information, and we transform it somehow, and it's going to be a linear transformation. That's the main type of function in a deep net. Okay, so how does that work? How does a linear layer work? So we have our input, which is a vector, and our output is going to be a vector as well. And the relationship between the two is going to be linear. So it's going to be each element of the output is a linear combination, a weighted sum of the elements of the input. So the parameters of this layer are called weights. That's the weights of this weighted sum. They can be positive or negative. And the output is just a linear combination with those weights. Okay, we often also will add this term called a bias, which is, now it's not linear, but it's affine, but we still call it linear just as a notational convenience. And we're going to say that the output is a weighted sum plus some offset. And this turns out to give some more expressive power to the layer. It's a good idea. Okay. So that's the basic linear layer. It has weights. I'm going to color the weights in blue and the biases in blue, indicating that they're parameters. So parameters are going to be blue. Okay, the parameters are the weights and the biases. Okay, maybe you've heard of a company called WANDB. Weights and biases is the name of that company. W and B, weights and biases. These are the parameters of a neural network. Okay, so we're going to fiddle with those parameters to achieve a particular transformation that will do well on our task. That's the idea. Okay, so that's layer type 1, linear layer. Layer type 2 is the point-wise nonlinearity. So what is the problem if let's say I had a neural net of only linear layers. I have a composition of functions. Every function is linear. What's going to happen? Well, composition of two linear functions is a linear function, so the entire network will only be a linear function. We're back with Rosenblatt, where people, and Minsky, who said, you know, Rosenblatt-style neural networks can only do linear things because he didn't have the nonlinearities interleaved with the linear functions. Okay, so what you need to do is you need to add a nonlinearity to make it so that you can do nonlinear things. So we call it a pointwise nonlinearity when it is a scalar to scalar mapping. So we take our output representation vector, and for every element, we're going to apply a nonlinear function, a scalar one number to one number nonlinear function. Okay, and the one you might start with, the one that was in the perceptron, is a threshold. It just says if the weighted sum of the inputs exceeds a threshold, then we will have our neuron fire. We'll have our output fire 1. And if it doesn't exceed that threshold, it will output 0. So it's kind of like making a decision. It's deciding, am I on or off? It's like a binary decision. OK, so let's see how that simple model already can do something quite interesting, which is linear classification. And then I'll get to this nonlinear, the ability to fit nonlinear functions. OK, so linear classification with a perceptron. So here's my perceptron. It's going to take two numbers as input. That's like 2 pixels it observed or 2 words it read in a sentence. It's going to take a linear combination, create another representation z, and then it will take a threshold to output a decision y. OK, so let's look at z as a function of the 2 inputs. So here's the values of x1 and the values of x2, the 2 inputs. And here's what z looks like if z is a linear function with a particular w1 and w2 have a particular set of values. So it looks like a ramp. Why? Because a linear function in high dimensions is like a hyperplane. It's some kind of flat surface. Okay, think of this as like a ramp, right? A flat surface. Now, if I take my threshold, I will simply threshold around 0. So 0 is this greenish color, and then if I threshold the values of z around 0 to create the values of y as a function of the inputs, I will partition the space in half. Okay, so partitioning your space of inputs in half is binary classification. So what does that look like? Here, let's say here's some data I want to fit. Some of my data is labeled 1 and some is labeled 0. My data is 2-dimensional data. x1, x2 is a data point. And here are where the class 0 lives, and here's where the class 1 lives. So I can fit a neural net to that data by fiddling with the weights and the biases, the parameters, until my neural net partitions the space into the top half of the space will be, the neural net will predict 1. It will assign the value of 1 because the training data is 1 up there. Okay, if I initialize with a bad neural network, it's partitioning the space in a way that doesn't match the data. So it's going to misclassify these 1s because it will assign them the value of 0. And it will misclassify these 0s. It will assign them the value of 1. Okay, if I fiddle with my parameters, that corresponds to changing the slope of this line. Okay, because I'm fiddling with the parameters going to change what the shape of this function is. It's a linear function. It'll just shift it up and down, and in high dimensions, it will take that hyperplane and shift it all around. That corresponds to changing how I partition the space in this linear fashion. And if I fiddle them to minimize my misclassification error, I'll eventually partition it like so. And it will correctly classify my training data, and that's how you train a classifier. OK. So far, we can do linear classification. There is one problem with this particular pointwise nonlinearity. Okay, it maps input scalar value z to output scalar value g of z, or y. And this is the shape of it. It's a threshold. If my input value is greater than 0, then my outputs will be 1. Otherwise, it'll be 0. The problem with this is I said that we're going to optimize these systems with gradient descent. So what is the gradient, the derivative of this function in these regions? Somebody shout it out. What is the derivative of this function in these regions? D output, D input. What do you think? I think some of you know it. Yeah, in the back? No? OK. Okay, I saw it, 0. Thank you. I think a lot of folks probably knew this, right? The slope of this function is 0. That's the gradient. Okay, gradient descent is all about optimizing systems with gradients. And if there is a slope of 0, that means that I have no idea what direction to walk to make progress. The gradient is 0. It doesn't tell me anything about should I change the values of z to be big or small to achieve my objective. Okay, so the problem is that the gradients are 0 in this nonlinearity. So that means that we call it not differentiable. It's really what matters is the gradients are 0. Okay. So instead, we'll use a threshold that has non-zero gradients. So it's like, it looks kind of like a threshold, but now we just kind of gave it a slope. So in this region, there's non-zero gradients, and I actually can make progress if I'm doing gradient-based learning with such a system. Okay, so this is the nonlinearity we really use. It's easy to implement. It was kind of popularized in the AlexNet paper. The gradient is 0 on this half of that function, and that it can be a problem, but it turns out it's kind of fine. It just means that some neurons, some of the neurons on my network might kind of die and turn off for certain inputs. But this actually has the effect of creating maybe sparsity in my representations. So it's not necessarily a bad thing, but this works in practice. And so this is called the ReLU, the rectified nonlinearity. The pointwise nonlinearity takes in an input neuron's value, and if the value exceeds 0, we just output that same value, and if it's less than 0, we output 0. And that's the shape of the function. Okay, so we have linear and ReLU, and those are the two main layers in neural nets. Okay, so now how do I compose a complicated network out of these simple layer types? So we have our inputs, and we have a linear layer. And now we will pass every output through my pointwise nonlinearity, a ReLU. And we'll call this vector a hidden vector. We'll call it a hidden unit. So the analogy is that each of these numbers is like a neuron that's turning on or off. But you can also think of it as just like a vector of a numerical representation of your data that's being processed. And then we will apply a new mapping with new weights. And we'll do this over and over again to create a deep network with a stack of transformations. Okay, and I was only drawing some of the arrows, so if you want to see the whole thing, like every single output unit will get a different linear combination of the inputs. And so the whole thing is this matrix that maps, an n-dimensional input to an m-dimensional output. Okay. And you add the biases by just multiplying the number 1 by the bias value. That's just a simple trick. Okay, so there's the math. It's just weighted matrix multiplied by the input plus a bias, passing that through a pointwise nonlinearity, and doing this over and over again with different weights and different biases on each layer. And the name for this such a system is a multi-layer perceptron. So it's not just one layer, it's 2-layer perceptron here. And the parameters that will fiddle and optimize with gradient descent are all of the weights and all of the biases in this network. Okay, so here's the big picture for the basic motif of a neural network, of a deep network. We have input, and then we have linear transformation, pointwise nonlinearity. Linear transformation, pointwise nonlinearity, and we do it over and over again. And convolutional networks, transformers, recurrent networks, residual networks, they all have this basic motif somewhere in there. And they add little other motifs on top of that as well. But it's always a sequence of linear, nonlinear, linear, nonlinear. Okay, we might have special layers at the end to read off our prediction, which I'll talk about in a bit. And here's what it looks like. Every layer is a function, and we just have this kind of composition of a lot of functions. Okay, so I told you that perceptrons can do linear classification. So how can we get a multi-layer perceptron, a stack of layers, to do nonlinear classification? We should be able to, because the pointwise nonlinearities give us that capacity, that flexibility. So here's how it works. Let's just make it 2 layers, right? So we have one layer, and then we have pointwise nonlinearity, and then we have another layer, another linear combination, and then a threshold at the very end. So we'll keep that threshold just to make our final decision. Okay, so here's the math, right? Matrix multiplied a set of weights by an input vector plus a bias, pointwise nonlinearity, that same operation but with different parameters, and then a threshold to make our decision. Okay, so here is now the visuals of what I have particular settings for the weights of W1 and W2. So if I change those weights, these pictures will change. But for one particular setting, here is the value of this unit as a function of the values that the inputs can take on. Okay, right? So what does it look like? Well, it looks like a ramp, but this part of that ramp is flat at 0. Why did it get clamped to 0? Because this unit is after a ReLU pointwise nonlinearity. So everything that was negative got clamped to 0. Okay, you can kind of work this out for the other units and see how there are all these little pieces, these little ramps that get cut off. Okay, so it's like ramp on the positive side of the function and then 0 everywhere else. You have all these little pieces, but then this here, H1 and H2 are these little, these like ramps that are cut off at 0. And then Z3, which is a sum of H1 plus H2, or a weighted sum of those two things, is going to be two of these funny little shaped objects summed. And then you get a more complicated shape. Now you get the ramps intersecting and they can create funny cones, okay? So what happens is if I want to classify a set of data which is labeled 1 in some cone separately from the zeros up here, well, there's no linear function that can do that. But when I add these two H's, which have these shapes, then I actually can create a positive region which has that more complicated shape. So an MLP with ReLU pointwise nonlinearities is able to do nonlinear classifications, able to assign labels of 1 to a nonlinearly shaped part of the possible input domain. And the particular shape is always going to have these, it's going to be angular. It's going to be piecewise linear, just because each of these pieces that you combine are linear functions thresholded around 0. Okay. A question in the back.
Sorry for the question. I'm really sorry, I have to apologize. But I'm following pretty well conceptually, but mathematically I'm a little bit slower. The graphic, so H1 and H2,
yeah.
If I combine those two in my mind, Z3 should be rotated 90 degrees left.
Good, yeah, great question. So you're asking if I just sum H1 plus H2 in your head, then Z3 doesn't quite look like that. I believe that's because this is a weighted sum, but the weights are not 1. It's like 1 plus -1. I don't remember what values I used, but that causes the rotation that you're seeing. Yeah. Okay. So let me summarize now these two layer types. These are the two workhorses of deep learning. They appear in all modern networks. The one is a linear mapping from an input vector to an output vector with weights and biases. And the other is a pointwise mapping from all the values in the input vector to all the values in the output vector with a particular pointwise nonlinearity. It has no parameters, no learnable parameters. So all the machine learning, all the fiddling with the parameters is happening on the linear layers. Okay, so these two things get stacked. And what does it look like when they actually transform data? So here's some pictures where I have my input space of data, and I'm drawing a grid of points in that space and seeing where they get mapped by the ReLU and the linear function. The linear is going to do this geometric transformation. It's like going to stretch and shear and scale the space of inputs. So I chose a particular set of values. I could have chosen other values, but this particular set of values will be like, we just like, rotate the input grid somehow. And if I apply that linear mapping to a distribution of data points, like a kind of cloud of data points, here's how it remaps them. And if I apply the ReLU, what it does is it becomes straight identity mapping in the positive quadrant, but in the negative quadrants, everything gets clamped to the axes. And so if I apply a ReLU to a distribution of data, I get most of the values getting kind of clamped to the axes in the output space. This is the kind of geometry of the mappings that deep nets are achieving. And at the end of this lecture, I'll show an example of how this looks when you use it to train, how these diagrams actually move as you train a real neural network. Okay, but you can think of the transformation of data points layer by layer as being these geometric squishes and pulls and rotations. And that's how the network takes your raw data and transforms it into a better representation. Okay. So summary number 2, is that the main layer types in deep nets are linear layers. There's a lot of special kinds of linear layers. We'll see convolutional layers, which is a special case of linear layers a little later, or related to linear layers. And there are pointwise nonlinearities. And the common motif is linear, pointwise nonlinear, linear, pointwise nonlinear, and so forth. OK. Any questions? OK. So yeah, this is a quick boot camp, and hopefully now you know the components of a basic neural network. The next question is, well, why are those good components, and what can you do with them? And here we're going to touch into a little bit of the theory of deep learning. And there's a lot more that can be said here, but I want to give you a flavor of it. So the first question, the first kind of theoretical question that you want to ask, if you want to see, is this a good architecture? Is this a good way of representing functions? Is to ask, what is the class of functions this can represent? Can this drive a car? Can this recognize cats and dogs? What can it represent? What can it do? OK, and the answer is it can do everything, roughly. OK, everything that's continuous. So this is a good answer to have, and it's a good property to have in a kind of class of functions that you would look at. And this is one of the reasons why deep nets are a good class of functions to look at. OK? So by the way, this is not that hard to achieve. Anyone know a different class of functions that has the ability to fit everything that's continuous? Anyone have an idea? Different class of functions? OK. Maybe it's a more advanced question, but polynomials. Maybe you actually learned this in like high school. A high order polynomial can fit anything. So neural nets are not unique in this sense, but it's an important property to have. We call it universal approximation. So let me give you a sense of how you can actually prove that neural networks have the ability to approximate any continuous function. OK? And what I'll do is I'll show you this scalar to scalar mapping from x to f of x via two linear layers and, three linear layers, OK? And there's pointwise nonlinearities, ReLUs, interleaved in between, which are not shown here. OK, so what kinds of functions can that network approximate? So the idea of showing that it can approximate anything is to say, first, we can approximate any curve with a weighted sum of little boxes. OK, this is something that you probably saw in high school calculus, like the idea of an integral being, you can approximate the area under the curve with a lot of little boxes. OK, so here's we're doing that, basically. We're saying that we can approximate any random curve with enough small little boxes. That's the first part of the argument. The second part is to say a ReLU MLP, so a basic neural network, can approximate a box. If a neural network can approximate a box, then a sum over a lot of such approximations will approximate any curve. That's the basic idea. OK? So here's the proof idea. We approximate a continuous function with an indicator function, a little bump. And then we will use a simple neural network to approximate a little bump. And then we'll take a combination over a lot of such little bumps to approximate the curve. OK. So can we actually approximate a bump with a neural network? Turns out not so hard. So here's a ReLU function, right? This is just what we already talked about, the ReLU. OK, if I take ReLU minus another ReLU, then I take a ReLU centered at 0 minus a ReLU centered at 1, then everything above 1, I get the negative, which is just going to cancel out the effect of the ReLU, and I'll get a shape like this. OK, so then if I subtract another ReLU centered at 3, now I'll get the negative ReLU after I reach 3. So it's like before I reach 3, it's just this component. Then in the middle, it's these two components. And then after, it's just this component. So it turns out that a sum of 3 ReLUs can do that. And a sum of 4 ReLUs, you can kind of make any shape you want, right? So now we got a sum of 4 ReLUs with different offsets. So ReLU x minus ReLU x minus 1, and so forth, will approximate a bump. we got our approximation to a bump. And in fact, if I put some parameters, mu and divide by gamma, I can arbitrarily scale the slope of that bump. So this is a construction that will get arbitrarily close to approximating a bump. And all it is ReLU neurons added together. And what are ReLU neurons added together? That's just ReLU followed by linear combination. Okay, so here's what we do. We transform our data by multiplying it by a value and adding an offset for each of these arrows. Okay, that will make x multiplied by a scale gamma, 1 over gamma, minus an offset, my bias, v minus gamma in this case, and that will be 1 neuron. I'll do that for 4 neurons because I needed 4 ReLUs to make a bump, and then I'll take a linear combination of them with these particular weights, and this is one little approximation to a single bump. And then I have one little bump, and I want to approximate the function with a lot of little bumps, and so I just need to do that n times for a function that has n bumps. And that's just another layer. So now I've hand constructed a 3-layer network that can approximate any continuous function if I have enough items in this ... here, enough neurons, enough bumps. Okay, so that's the basic proof, and you can actually find simpler constructions and so forth, but they require a little bit more math. So this is an easy one to construct that shows universality. Okay. Questions about that? Simple construction that shows that a neural network with enough neurons can approximate any continuous scalar-to-scalar function. Okay. So that was a 3-layer network, and you can approximate any, in this case, scalar-to-scalar function. You can also show that similar constructions can approximate any multivariate function as well, but it takes more units. Why do we make nets deep? Okay, I just want to give you a flavor of the idea. Empirically, it turns out that deeper nets do better, and everybody likes to make nets as deep as they can. Is that justified? It turns out that there's some beginning of a theory that does justify that. And the basic idea, well, first it works better in practice, that's the main argument. But the theoretical argument is that for some functions, to approximate them well with a neural network requires a very, very large number of neurons, an exponentially large number of neurons. But if you just have a shallow net and you keep on adding more neurons to it. But if you have a deep net and you keep on stacking neurons in depth, you can get away with a linear number of neurons to achieve the same approximation. Okay, so this gets to one of the kind of basic questions when you design neural nets, which is width versus depth. Depth refers to how many layers of transformation you have in your network, and width is how many neurons you have on each layer. Okay, so more neurons is more width, and more layers is more depth. Okay, so the empirical observation is oftentimes you would prefer to have more depth as opposed to more width. This depends on the exact setting, but there are certain advantages to depth that cannot be achieved strictly by width. Okay, so this is kind of one of the big questions when you're designing a new architecture. And here's a sketch of the idea for why depth can be useful. Imagine that I want to approximate a really bumpy function like this. Well, with my construction I showed you before, I would need that many units to make that many bumps. But it turns out that if instead of doing the construction I showed, I instead added more layers in depth, the layers in depth can take however many bumps you have, and on the next layer it can double them. They can do this kind of sharding of the space. That means every layer I add doubles the number of bumps, as opposed to just every unit I add can match one more bump. So neural networks, ReLU networks, are piecewise linear. They look like this, okay? And they can have as many bumps in a way that's bounded by the number of units in depth and width. Deeper and wider networks can be more wiggling. They can have more bumps. And the number of bumps that you have increases linearly with width and exponentially with depth. So this is one of the reasons why deep nets have some advantages over shallow nets. Okay, there's a lot more to say about this, and if you really want to see proofs of this property, then you'll want to read in more detail these slides from Francois Fleuret. Okay, or the papers that he references. Okay, a technical name for that study is called depth separation. Really interesting area, but technically pretty advanced. Okay, so that tells me that neural nets can fit all kinds of bumpy functions. But the next question is, why is fitting a bumpy function enough? Why would, if I train my network to fit my training data really well, no matter how bumpy and complex is the fit to my training data, like it actually will predict the right label for every image, or it will actually, do exactly what I told it to do on the training data. Why would I expect that to work well on other data, on test data that I did not fit to? Okay, this is something that to fully appreciate, you have to have some background in machine learning. But the basic theory of generalization says that if I have a really complex function, and I fit that to my data, it might overfit to that data and not generalize well to new test data. It'll kind of memorize my training data, but it won't actually work well on new scenarios. It won't. I'll train it really well on fish and grizzly bears, but then I show it a grizzly bear in a new environment that's never seen before. It will have no idea because it's only memorized just training data. Why do deep nets learn rules that generalize, that don't just fit their training data in this like perfectly universally approximatable like fashion, but actually generalize? Okay. And they do learn rules that generalize. That's the empirical observation. That's why we actually use these things, why they're so popular. And it defies classical theory in a certain sense, because neural networks have a lot of parameters, and classically you'd expect that they would overfit and not actually generalize. Okay? So there's kind of an emerging hypothesis around this that I'll summarize as the simplicity hypothesis, and that's that even though deep nets have a lot of parameters and could find really, really complicated fits to the training data, they don't. So the classic theory says big models learn hopelessly complicated functions that overfit the data. But the emerging theory says, well, deep nets do have that capacity, but they actually fit the data in a way that generalizes. And there's a deep connection between simple fits to data and rules that generalize. It's called sometimes it's called Occam's razor, right? The idea that the best explanation for the world is the simplest one you can come up with. And so my intuitive understanding for why deep nets generalize is they don't just fit the data, they find the simplest or a simple fit to the data. And there are some interesting emerging theoretical papers on that property. Okay, so yes, deep nets can find really complicated wiggly functions, but in practice, they will tend to find a simple function that still fits the data well. Okay, so summary of this section, which is a bit more the theory of deep learning, is that deep nets are universal approximators. Deeper nets can approximate more complex functions, and there's an exponential advantage of depth. And a kind of ongoing scientific and theoretical question is, why do deep nets generalize? And a current hypothesis that's being developed is that it's because they actually find simple fits. They somehow embody something related to Occam's razor. Okay. Okay, questions there, yeah. Okay, yeah, in the back.
If there's another one, it's all good, sorry.
No, go ahead.
I was going to ask, is that simple fit theorem partly because if you're using the gradient approach, you're never actually finding the global minimum. And so when you have all these kind of like localized minima, which are relatively accurate,
yeah,
you have lots of them, you do actually have these boundaries of misclassification which actually end up being very simple and generic.
Yeah, so I think the question is, could the generalization properties of networks be due to you're not finding the global minimum, but you're finding a local minimum, and maybe that has a more a property that will kind of regularize the system, or it'll be simpler somehow than the global minimum. And yeah, I think that's nearer to some of the current working hypotheses that the dynamics of gradient descent are partially responsible for the fact that the network finds not just a memorizing solution, but a solution that generalizes. And so we can talk more about that offline, but yeah, the kind of dynamics of gradient descent are thought to be related to this. Okay, But this is very much ongoing science, by the way. It's not, we don't have like full proofs of that. Yeah. A question in the, yeah.
Isn't the success an indication of some sort of continuity, and I don't know exactly how to define that term, in the real world? Because if I were to take a bunch of random patterns and say, this is a type 1, that's a type 1, that's a type 1, then I've got a bunch of other random patterns that I call type 2, and there's really purposely no similarity between the elements of the
Yeah.
type 1 set, then it wouldn't work, right?
I think that's exactly right. So I think the question is, isn't the success due to something about the structure of the world and the fact that the world might have continuous or simple structure? And I think that that is true. I think you can make these no free lunch arguments that there could exist a world where deep nets wouldn't work. But we happen to live in a world where the inductive biases of deep nets and the preference towards certain kinds of simple functions match something about the way the physical world works. And I think that's, yeah, a deep and interesting argument, yeah, to make. Okay, one question, then I'll have to move on. Yeah. Oh, go ahead. Yeah.
So it's about usually when I read paper, it says, okay, so this vector network has how many layers? And then recently I read a paper, it says, okay, so we use a 3-layer, a 4-layer ML. And then I'm thinking, so MLP is a unit, or how, what's the difference between like normal layer and
So MLP just refers to a neural network that is linear ReLU of any depth. And then sometimes people will talk about, they'll call that a module. They'll say, I have an MLP that's 5 layers deep, and now I'm going to take 5 of those and make an even bigger network out of MLPs as subcomponents. Like the MLP can be a subcomponent of a bigger meta network, and like, transformers are an example of that. Okay, so here's the deep net, and I didn't quite talk about how you'd actually use this to read out a classification. I want to touch on that a little bit in the last section of this lecture. Okay, so at the very end of the network, we will have a vector of numbers, right? Because all the neurons are just numerical values, and we'll have a vector at the end of the network. That's my final kind of representation of the data, but we'll give it a special interpretation. We'll call each of the elements as a score. Sometimes these are called logits. A score, which is like the score of how much do I think the input image is a clownfish or chameleon. And the way we'll train this network, and then we'll decide on the label by just taking the argmax of this score vector. So we thought the score for clownfish is highest, and so we'll say it's a clownfish. And then how do I make it so the scores actually correspond to reality, correspond to the training data? Well, I simply give myself a big loss if my score I put on clownfish is wrong. So if I put a low score on clownfish and the label is clownfish, I'll say I better update my parameters to get a better, higher score on clownfish. Okay, so right, if the network says I think it's a clownfish, I put a high score on clownfish, but the ground truth label in my training data was grizzly bear, I'll say that's a big loss, and I better update my parameters to avoid that. Okay, I'll update them via gradient descent. Okay, so here's numerically how you do it. You compare your output score vector, your output vector of logits, to your ground truth label in your training data, where the ground truth label is represented as a score vector that puts 100% score on the true class. The human has labeled, this is a grizzly bear. You should have put 100% score on the grizzly bear. You put 90% score on clownfish, so you're wrong. And we'll just take the difference of these two vectors, and we'll sum up all the errors that we incurred. Like we said, this was wrong, you should have said 0. This is wrong, it's not an iguana, you should have said 0. You should put 0 on grizzly bear, that's wrong. You should put 100%. So you take the difference of those vectors, you sum up all those errors, and that is your loss numerically. So some technical terms for this. This is called a one-hot vector. It's a vector that represents my ground truth label. And this comparison, where you just sum up the differences between these vectors, is called the cross-entropy loss function. So if you've heard of those terms, that's the connection to make. But it's very intuitive. Okay, there's a log in there, but don't worry too much about it. Okay, so here's kind of what it looks like. You think of your output of the network as a set of numbers that represents the probability that you think the image is what one each of these classes. And then you compare the probability that you output to the ground truth probability, which is known because the human has labeled it. It's a clownfish. It's 100% clownfish. You know, a human could have labeled it as saying, I don't know what it is, but in this case, we assume the human is like certain. They know exactly what it is. And then you compute the difference. You just take the difference between these things. You take the difference in a funny way. You actually take a pointwise multiplication, but don't worry too much about that. We just say we should have put, you know, we only put 50% probability on clownfish. We should have put 100%, so we incur an error of, you know, all that red region is the amount we could have actually placed on clownfish, and that is the error under this particular cross entropy loss function. Okay. So the name for this whole thing would be a softmax cross entropy classifier. I'm not going to go through all the details of what those terms precisely mean, but if you hear that, that's the most common, you know, machine learning 101, deep nets 101 loss function type of problem you'll encounter. And so now you know that it's really just saying, make my output vector place high score on the true class. Okay, so if my output is grizzly bear, I predict it's a grizzly bear. Well, I said it was 80% likely to be a grizzly bear. It's actually a grizzly bear, so I could have said it was 100% likely, and that's my error. And I'll update my parameters in my neural network F, the weights and biases, until I achieve the lowest possible loss. In this case, placing 100% on grizzly bear. Okay. Same, you know, chameleon is another case. Okay, so to train a deep net classifier, and by the way, this is what you'd have to do for the training algorithm for classification. For other types of problems, you'd have a different particular loss function and way of kind of mapping your outputs to the ground truth labels and comparing the difference. But this is for classification. Okay, so to train a deep net, to do that, you know, we'll fiddle with all the parameters until we minimize that loss to correctly call this whatever the human labeler has called it. Okay, and we'll usually do this over a big training data set of a lot of images with labels. And one of the tricks in deep learning, now we get to kind of the data structures of deep learning, one of the big tricks is to do all the operations in batch. Okay, so rather than saying, what do you think this is, network? Okay, you got it wrong, it was supposed to be chameleon, update your parameters. We instead pipe in a bunch of images at once, run them all in parallel, and the reason we do this is because the hardware we have, the computer hardware we have, is good at doing parallel operations. So on your GPU, which is the part of your computer that will process deep nets, you will be processing a whole stack of images at once, making a whole stack of predictions, comparing that whole stack to the labels, and doing gradient descent to update the parameters. Okay, so if we look at the stack, the basic data structure that you'll see in code all the time is going to be a data matrix where I can extract my representation of my inputs on some layer of my network. I can stack them across all of the images I'm processing, all the data points I'm processing, and we get this matrix of data by features. So you might call this a data matrix. And you can look at that, how the network represents the data on different layers. So this is the data matrix for layer 6 of this network. Okay, so you can think of this as like on layer 6, the fish is represented by a vector of numbers, and maybe those numbers are representing attributes of the data. This is just a possible interpretation. And people do go and probe those representations and see what they're actually representing, and they do often have kind of semantic meaning to a degree. But every layer of your network processing data is going to be processing a batch of inputs and extracting, you know, features from those inputs, which are just the vector representation of the data. Okay, we call this a tensor, and so when we get to the PyTorch at the end of this session, we'll see that PyTorch is all about just tensor processing. So everything is a tensor. Okay, we have our inputs, which are in this case just two numbers, not an image, and we have our batch dimension, which is, you know, we'll have a lot of data points. Each data point is two-dimensional, so data by number of features of the data. And then we'll have a weight matrix, which is going to be a matrix. It's also a tensor. It's a two-dimensional tensor, a matrix. A tensor is just a multi-dimensional array. And then we'll multiply every item in the batch by this matrix to get a new representation Z1, Z2 for every item in my batch, every data point. And so everything is just a tensor. Everything is just linear algebra and tensor algebra. Okay. So takeaway from here, the basic data structure in deep learning is the tensor, the multi-dimensional array. Data on each layer is a tensor of data points by kind of current representation of that data. And deep nets can perform image classification by making it so their output tensor, their output representation of those data points matches a representation of the truth, which in that classification case is a one-hot vector. It's a data matrix with a 1 on each row has a single 1 in the location of the true label of the data. And you're just trying to make that output of the network match that ground truth. Fiddle with the parameters until that happens. Okay. So the very last thing I'll show just quickly is what does this actually look like to train a classifier. Here I have two-dimensional data. I have red points and blue points. I want to classify between them. It's a nonlinear classification problem because there's no line that separates these two distributions of data. Okay, so the neural net we're going to think of as linear transformations of the data, pointwise nonlinearity. It's like a series of geometric transformations of the data. And the output should be one-hot vectors. All the red points should be the vector 1, 0, and all the blue points should be the vector 0, 1. Okay, so a representation of the labels is I want all the blue points to have the label 0, 0, 1, the one-hot vector that represents the second class. And the red points should go here. And geometrically, what the neural network is doing is just layer by layer moving around these data points until they match the target output, which is correctly segregating the classes into these two one-hot vectors. Okay, so here's what it actually looks like if I train this. Nothing is hidden here. This is a network with linear, ReLU, linear, ReLU, linear, and then at the end is just a mapping called softmax. And the data on every layer is represented as two-dimensional vectors. So the width of every layer is two dimensions. And here's what it looks like to train it with gradient descent. Okay, so what happened is these little lines are like the linear geometric transformation. It can shift and scale and rotate. That's what linear transformations can do. Then the ReLU squishes everything down, and then we get another shift and shear, and then things get squished down by the ReLU again. The softmax just kind of is another nonlinear mapping. It kind of stretches everything out. And at the end, the red points are heading toward this corner, and the blue points are heading toward that corner. The blue points are heading toward the label 0, 1, and the red points are heading toward the label 1, 0. And that's all that's happening. The network is fiddling with its weights to make these linear transformations stretch things in such a way that the red points get segregated to one label and the blue points get segregated to the other label. I'll show it one more time. Okay, those are steps of gradient descent. Okay, so more complicated networks have much higher dimension, many more layers, other tricks, but they're all operating in some fashion like this. Okay. And this is just a visualization of, a very fancy network that can take all kinds of different mixed up data points in the input and segregate them into clearly different classes. This is the CLIP neural network visualized in the same fashion. Okay, so I think that, I'll just wrap up now. So yeah, what we've seen a few different things, but let me just quickly comment on what does deep learning mean. So one is that it's this architecture, linear, pointwise nonlinear, linear, pointwise nonlinear, these stacks of simple functions, and people keep adding more motifs on top of that over the years, which Kai-Ming will talk about. Another perspective on neural networks is it's this kind of philosophy of writing functions as compositions of simple pieces, which all can be optimized jointly with gradient descent. And it's kind of like you're not explicitly programming, you're doing something that we might call differentiable programming. You're programming partial solutions and then letting gradient descent fiddle with the parameters to achieve a good outcome. I should also mention that the name for gradient descent as applied to deep nets, the particular way of applying it to deep nets is called backpropagation. So if you've heard that, in this lecture, I've just always referred to it as gradient descent, but you might hear the name backpropagation to refer to that process. Okay, and some other key concepts associated with deep learning is the idea that you have a hierarchy. You have features that are extracted layer by layer, and at the top you have a more abstracted representation of the data. At the bottom you have a more shallow, superficial representation of the data. This idea of reuse is common in deep learning, that we don't train everything from scratch. We get representations, then we reuse them over and over again. And then another big concept associated with deep learning is that things start to work at scale. And a lot of the current ongoing work is just how do you make models that work really well when you scale them up. When you train them on more data, how do you get hardware that efficiently can do things at scale? And that's a concept very associated with deep learning as well.